All right, so let me get right to the main point. Design libraries on top of elegant mathematics. If you don't get anything else out of this talk, that's what you should get. And I hope that mostly I'm preaching to the choir here. I think we all know reasons for this. Some reasons I think will become apparent later. It leads to less code, and it leads to better insights into the structure of your library. So I'm going to tell you a particular example of this, sort of a success story, if you will. I have this library called Diagrams, and it's built largely on top of this theory of monoids. So I'm going to tell you about monoids later, but let me first tell you a little bit about diagrams. So diagrams is a domain-specific language. It's embedded in Haskell, so diagrams programs are just Haskell programs, really. And it's designed for producing vector graphics. So here's an example of the sort of thing you can do. Here's a little program, so you see we have some kind of primitives like a circle. You can give things attributes. You can import images. Here, this is actually just an operator that says to put two diagrams one above the other. So here we say put the circle on top of this picture. There's a lot of cool things that people have built using it, so here's just a few examples, just to give you a flavor for the sorts of things you can do with it. Okay, and there's more examples you can find on the web. I'll give you the URL later. But so, what are diagrams? This is the first question we have to answer when designing a library. So there's a lot of ways you can answer this. The answer that I've chosen is a diagram is a list of primitives. A primitive is some sort of primitive shape that's very simple that we know how to render, we know how to work with. And a diagram is just a list of these, which corresponds to sort of stacking them all on top of one another. So you'll notice there's, I don't know if you can actually see it, but there's this little red dot in each one of these. So every primitive, every diagram has this notion of a local origin, the origin of the vector space that it sits in. And you just reason about everything locally. And when you put two things together, you just superimpose their local origins and combine them into one. Okay, so this is the semantics of diagrams. And the paper starts with this as the actual representation, as a very naive representation of these, and then makes a bunch of incremental transformations in order to support the kinds of features that we want to support. What are some of those features? So here's maybe represent some diagram that you start with in the middle. Here's just some of the things you can do. You can apply arbitrary affine transformations like translation or other scalings, rotations, things like that. You can combine it with other diagrams either by superimposing them or, as we've seen, by sort of putting them next to each other. You can query points on the boundary of diagrams and use that to put things together in various ways. And of course, you can specify attributes. So the paper talks about all of these and sort of talks about how to build up a representation that supports them. In this talk, I'm just going to focus on this one feature of being able to put diagrams next to each other. Okay, so really this will be composed of two things. One, I'm going to talk about constructing monoid instances compositionally, and then I'm going to talk about monoid homomorphisms, what those are, and what that has to do with this idea of putting diagrams next to each other. Okay, so what's a monoid? Probably a lot of you already know this, but just a quick review. It's a type that has some binary operation called mappend, and some distinguished element called mempty. And I'm going to use this notation, the little diamond operator for mappend and an epsilon for mempty. And of course, there's some laws that monoid instances have to satisfy. So the binary operation should be associative, and the epsilon, the mempty, has to be the identity element for that binary operation. And the fact that the binary operation is associative means that we can unambiguously write the combination of a list of things, and in fact there's a function called mconcat that does this. So what are some examples? One very standard example that I'm sure we've all seen is lists. So concat operation on lists is associative, that's the combining operation, and the empty list is the identity. Okay, but we already said that the semantics of a diagram is a list of primitives, so that means that diagrams inherit this monoid structure from lists. So putting two diagrams together just corresponds to concatenating these lists of primitives. And what does that mean? Well, since the primitives are thought of as stacked on top of each other, this just corresponds to taking two diagrams and superimposing them one on top of the other. And the empty list would correspond to some sort of empty diagram that when you superimpose it on top of some other diagram, it doesn't change it. Okay, here's another example. If we have some kind of ordered type, you can imagine using the max operation to combine two things of this type. And that's certainly associative, that's not hard to show. But is there something that we can use as the identity element? And actually, in general, no. So if you think about some kind of unbounded type like integer, the identity element for max would have to be the smallest possible integer, so that when you take the max of it with something else, you always get that something else. But there is no smallest integer, so that doesn't work. But this is still a useful sort of structure, that we have this associative binary operation on max. And so this is actually something called a semigroup, which is exactly what you'd think. It's like a monoid, but there doesn't have to be an identity element. So this will come in handy later. Just to point out that not everything is a monoid, but there's still this useful structure we can look at. Okay, so now back to how are we going to support these operations that we want to support. In particular, this operation of putting two diagrams next to each other. So, how does this example work? How can we actually implement this? We apparently need to be able to compute some sort of bounding information about these two diagrams in order to know where to put them so that they fit next to each other. So the first idea we might have is to use bounding boxes. Lots of things use bounding boxes. Maybe this will work. Certainly, if we had bounding boxes, we could use those to put two diagrams next to each other. But this turns out not to work very well for a number of reasons. One of which is, if we want to be able to arbitrarily transform diagrams, it's not clear what should happen to the bounding boxes when you apply some transformation. So here I've applied this rotation to this diagram, and what bounding box should I get out? And remember, this could be some arbitrarily complicated thing. So I can't recompute the bounding box. I have to be able to compute the bounding box given only the old bounding box. And there's not really any good answer here. So a much better solution is something called envelopes. So let me explain how these work. So consider this ellipse here, some diagram, representing some diagram. The envelope is a function. It's given as input some vectors, which are taken to emanate from the local origin. And as output from this function, it gives the distance to the nearest perpendicular line that is sort of a bounding line that contains the diagram on one side of it. So if you ask in this direction, you get this distance. In this direction, you get this distance to this perpendicular line here that's tangent to the ellipse. This is just another example to sort of just to show it sort of in more generality. If you query it in this direction, this makes sense. We get this bounding line here. In this direction, notice actually we're getting a negative distance out because this perpendicular line here encloses the square on this side of it, since we're querying in this direction. If we query in the other direction, we get this line down here, right? So it doesn't make sense actually to get negative distances out. And it doesn't even need to be a special case. That's just sort of like, that's sort of the obvious thing to do, and it works out nicely. Okay. So that's the definition of an envelope, but how do we compute these for a diagram? Sorry, I should say, we can represent this, we can write it down in Haskell by this. We can make a new type, and we suppose that we have some type v2 that represents two-dimensional vectors, and something representing the real numbers, which of course we don't actually have, but I'm just going to pretend that we have a nicely behaved real number type. Okay, so just pretend. Okay, and we can actually use this to put diagrams next to each other, right? Because here's how we do it. We query the envelopes in opposite directions along the direction that we want to compose them. We get some distances out, we add the distances together, and that tells us sort of how far apart to place the diagrams. Okay. So, how do we actually compute these things? So, we'll begin by assuming that we do have a way to compute envelopes for primitives. And that makes sense, because the primitives are simple things, you know, circles, line segments, whatever. We can sort of mathematically derive, okay, what's the proper envelope function for these things? So given that, how do we compute the envelope for an entire diagram? An entire diagram, remember, consists of a list of these primitives. So we could apply this, we could compute the envelope of each primitive, and then somehow we have to combine them together to get an envelope for the entire diagram. Combining together a list of things. Sounds kind of familiar. So what if we could make a monoid instance for envelopes? Then we could combine them all together using the mappend function, or the mconcat function, actually. Well, let's see. What would it mean to combine two envelopes together? So here I've got a square and an ellipse that I'm composing together. Suppose I already know their envelopes, and I want to figure out what's the envelope for the combined thing. Well, if I've given some input vector here, I just take that vector and I pass it as input to each of the envelopes of the component diagrams, and then I take the maximum distance of those two, and that's going to give you the distance to a line that encloses both of the composed subdiagrams. Okay, so apparently I want to sort of take some pointwise maximum over these two functions. Okay, so I'm sure we could now go off and write that down in some code. It wouldn't even be that hard, but let's not do that yet. Okay, let's think about this a little harder. So there in fact is a way to take a monoid instance for some type A and lift it up to be a monoid instance for a function type e to a. And here's how we do it. The identity element is just the constant function that returns the identity element for a. And to combine two functions of type e to a, you return a function, given an input e, it passes it to both of the input functions. Those both give us a's, and then we can combine those a's using the monoid instance for a. And it's not hard to prove that this in fact satisfies all the laws, etc. Okay, so that's nice. So remember, this is the representation that we had for envelopes. It's that they're these functions. And now we know we can make a monoid instance for functions as long as we have a monoid instance for the result type of the function. Okay, but there's actually lots of monoid structures you can put on the real numbers. You can do addition, multiplication, right? But actually what we're doing is we're taking a maximum, right? That's the operation that we're using. So to indicate that to the type system, we can add this max wrapper that we saw earlier. Okay, and now, using GHE's cunning generalized new type deriving feature, we can just write deriving monoid, and it'll take the monoid instance for this function type and lift it up over the envelope and give us a monoid for the whole thing. Except wait. If you're paying attention, you'll remember that max actually is not a monoid. It's only a semigroup because there's no identity element. So we can write deriving semigroup. This does work. We can't write deriving monoid. And but actually this is really interesting because it wasn't immediately obvious, just looking at the definition of an envelope, whether there was any sensible monoid instance. But now we can see there really isn't, and we sort of, the compiler can even tell us there isn't. If we tried to write deriving monoid, it would say, nope, can't do that. Okay, but we really wanted a monoid instance for envelopes because, I mean, we have these empty diagrams, and we'd like to be able to assign some envelope to them. So what do we do? Well, we can take some inspiration from the Grinch. So we can turn any semigroup into a monoid right, the problem is we don't have an identity element, so we just add one. So adding some distinguished element to a type we can do with maybe. And we just treat nothing as the identity element. And then if we have two justs, we combine them using the underlying semigroup structure. Okay, so now we can just stick a maybe in here. And if you're familiar with the Grinch, actually the dog's name really is Max. So this is great. So we just stick this maybe in here. So this means that now an envelope is either this special empty envelope, or it's a non-empty envelope that's represented by a function. And now we really can write deriving monoid. And we still haven't actually written any code. Okay, we've only written down some types and then gotten GHC to write a bunch of code for us. Well, not just GHC, but also some standard libraries. There's code there that we're just using bits of by sort of picking out which bits we want to use by writing down the correct type. So that's really nice. And this is what I mean by sort of building up these structures compositionally. Okay, and now of course it's easy to see how to compute an envelope for a whole diagram. We just compute the primitive envelopes and then use mconcat to combine them. Okay, so this is nice, but there's still one problem, which is that this is actually can be rather inefficient. So if you think about if we took this diagram and we computed its envelope and we used that information to figure out how to combine it with some other diagram. And then maybe we wanted to compute the envelope for that new combined diagram. We now have to recompute the envelopes for all these primitives and recombine them. And in some sense, it seems like we're duplicating work. So can we do better? So the answer is we can, sort of, and I'll explain what I mean by sort of in a minute. So the idea is, what if we could cache the envelope of a diagram along with the diagram, so we didn't have to recompute it every time? How could this possibly work? So here's the idea. We have a pair of a diagram and its envelope. Then the question becomes, what happens if we take two of these diagrams with their cached envelopes and combine them? Can we do something sensible with the cached envelopes? So let me first point out there is a way to make a monoid out of any pair, as long as both of the component types are monoids. You just do everything pointwise. It's actually kind of the same as a function instance, like a function from bool. This would kind of be the same thing. So what does this look like if we take these pairs of diagrams paired with their cached envelopes and combine them? So here I have a pair that has some diagram D1, and this is, I'm using this to represent like the envelope function applied to D1. So this is like the result of the envelope function. And I combine these two, what happens? Well, I combine the first elements, I get D1 combined with D2, and I combine the second elements, and I get this. But what I really wanted was this. I want D1 combined with D2, and the result of applying the envelope function to D1 combined with D2. So for this to work out, these need to be the same. And in fact, functions with this property have a name. They're called monoid homomorphisms. So a monoid homomorphism is a function that preserves monoid structure. It maps between two different types with a monoid instance, and it preserves the structure. And it turns out that yes, indeed, the envelope function is a monoid homomorphism, which is not actually that hard to prove, and you can see the proof in the paper. But that means that yes, we can cache envelopes along with diagrams like this, and it all just works out. And we still, in fact, even just say deriving monoid. And now it combines the diagrams, it combines the envelopes, and we know that that will do the right thing with the envelopes as well. All we need is this way to sort of inject a primitive into a diagram by calling the function to compute the envelope of a primitive. And that's really all we need. Everything else we get from this derived monoid instance. So I've really just told you sort of two of the, I think there's like 10 variations in the paper. So there's a lot more cool stuff about how to support transformations on diagrams, about something called monoid actions, which comes up when you're talking about transformations. And then really moving to a more efficient representation, not with lists of primitives, but of these trees that are in some sense derived as sort of free algebras over these monoid and monoid actions. So thanks very much. There's some code associated with this talk in the monoid extras package, and also these tree things are in the dual tree package on Hackage. And if you want to know more about the diagrams project, you can visit the website. Check it out. Thank you.